In this video lecture, I am going to discuss the topic of integration by trig substitution, which is basically a way of integrating something like this that we don't have really a technique for. And it combines two methods or techniques of integration that you should already be familiar with. One is integration by substitution, and the other is trig integrals. So ultimately what we're going to do is we're going to make a substitution, and the part that we're really focused on is this. When we have something of this form, we have the square root of a number minus a function squared, or it could be also something like the square root of 9 plus x squared, or maybe the square root of x squared minus 9. Something like that. When we have something like that in the integrand, that's where trig substitution will be useful to us. And the idea is that we will relate the number and the function via a right triangle and find a trig function, since we know that with right triangles the trig functions, sine, cosine, tangent, and so on are in play. And we'll use that with the Pythagorean theorem to find a substitution for, in this case, x. So in these general cases here, a is our constant, and u is some function of x. So let's just take a look at this first example. This is probably the most basic one, where I have u on the opposite side and a on the adjacent side. So by the Pythagorean theorem, we know that the hypotenuse is the square root of the sum of the squares of the sides. So the square root of u squared plus a squared. So something like this, then u would just be x, and a, since this is a squared, a would just be 3. It would be the square root of 9. All right, so that would be, and here, so okay, there's our hypotenuse. So what trig function are we going to use? Well, ultimately, we want to solve for u, right? We want u to equal something. So the easiest is to find a trig function where u is in the numerator and a is in the denominator, to avoid this more complicated. And we could use sine, and that would give us u over this, but that gives us kind of an ugly thing in the denominator. So the easiest is, let's just use tangent, because we know that's opposite over adjacent, and it makes it easy to solve for u. U equals a tangent of theta. So if we have something like this, where I have the square root of the sum of two squares, then this is the substitution that I'll use. Alternatively, we could have a scenario like this, where u is on the opposite and a is on the hypotenuse. All right, so again, first thing is, let's use the Pythagorean theorem to solve for this side. All right, so without going through all the details, that would give me the square root of a squared minus u squared. You can verify that, because if I square this and add them together, I get a squared, which I should by the Pythagorean theorem. So again, we want to take the ratio of u over a, because that makes it easy to solve for u. So what trig function would allow us to get this ratio? Well, that's going to be opposite over hypotenuse. We know that that's sine of theta, so that u equals a, just multiplying both sides by a, we get u equals a sine theta. So if I have something of this form, where I have a number minus a function squared, then this is the substitution that I'm going to use. And notice that's actually what I have here. Here's my number minus a function squared. So we'll come back to this example and think about how to set that up using this substitution. I just want to go over the last one. So in this case, u is on the hypotenuse, a is on the adjacent. That's going to give us a third side using the Pythagorean theorem of u squared minus a squared. Again, you can verify, if I square this and add a squared to it, I get u squared, which is the hypotenuse squared, which is what the Pythagorean theorem tells us. So again, I want to set up, I want a trig function that will give me u over a, and that's going to be hypotenuse over adjacent. So that's secant. Secant theta equals u over a, so u equals a secant theta. So again, if I have something of this form, so maybe like x squared, the square root of x squared minus 9, then this is the substitution I would use. So let's come back to our example. We already said it was going to be sine of theta. Let's come back and look at then how we would work this out. So I want to actually set up my triangle with these specific, a is just a general constant, and u is just a general function. So let's set this up with those specific. We know that, u is going to be x, so that's going to be x. We know a is going to be 3 because it's the square root. This is basically we have this form, a squared minus u squared. So over here, I know that's going to be 9 minus x squared, and that's going to be 3, right? Because that's just a, this is a squared. Okay, so here's theta. So this tells me that sine of theta will equal x over 3, so x equals 3 sine theta. That's my substitution. And then we know with substitution, we also need to find that we need to substitute for dx, right? So if I take the derivative of this, that's 3. The derivative of sine theta is cosine theta, d theta. All right, so let's just go ahead. I'm not going to actually work out the integral, but let's go ahead and do this substitution. So I'm going to end up with the integral. I know that dx is 3 cosine theta, and I'll just bring the d theta out here. And then x squared is just going to be 9 sine squared theta. And then I'm going to have the square root of 9 minus x squared, which is 9 sine squared theta. Okay, so I'm going to need to do some simplification here. But what I've done is I've taken something that I don't know how to integrate in terms of x, and I've done a substitution with, once we do some simplification here, this reduces to a trig integral that we know how to evaluate. So that's the basic idea. We'll look for one of these 3 forms. So notice this is the only one where there's plus, and that leads to tangent. Here, these two look similar in the sense that they have subtraction, but when the number is first in front of the function, then we end up with sine, and when the function is first subtracting a number, we end up with secant. All right, so let's just do a couple more examples, and we'll work out the details that we didn't do in this particular case. All right, so let's see. I had some examples already ready to go here. There they are. Okay, so let's take a look at this one. So this is a definite integral from -1 to 1, square root of 1 minus x squared. So again, let's go back, let's refer back here. We have 1 minus x squared, so that's a number minus a function. That looks like this. So let's go ahead and set up our triangle then. So we know that x will be here, 1 will be here, and this will be the square root of 1 minus x squared. And the reason I know that is just keep these handy and become familiar with these different forms. All right, so we see that, again, function goes in the opposite, the number goes, or the square root of the number, I should say, and the square root of the function go on the opposite and the hypotenuse, and then we have that on the adjacent side. Okay, so that tells me that sine of theta equals x over 1, which is just x. So that is my substitution. So dx is going to be cosine theta d theta. Okay, so we can go ahead and plug in. So I'm going to go -1 to 1, square root of 1 minus sine squared theta, and then dx is cosine theta d theta. All right, so by the Pythagorean identity, we know that 1 minus sine squared is cosine squared. So -1 to 1, I have the square root of cosine squared theta times cosine theta d theta. Well, the square root of cosine squared is cosine, times cosine gives me cosine squared. So I've got -1 to 1, cosine squared theta d theta. All right, and now we can use our double angle identity. And again, this goes from having some familiarity with trig integrals. Remember that cosine squared equals 1/2 1 plus cosine 2 theta d theta. So I can bring the 1/2 out, and I will get the antiderivative of 1. That's just going to give me theta. And this, I won't go through the details of it, but that's going to give me plus 1/2 sine of 2 theta. And that would just be via a substitution that u equal 2 theta. But again, if you should at this point have enough experience with trig integrals to be able to work that out. So I'm not going to work out the details on that. We're going from -1 to 1. Now remember, these limits are in terms of x. So we're going to have to go back to x in order to plug them in. Alternatively, we could have changed them in terms of theta, but it's kind of 6 one way, half dozen the other. So let's go ahead and move these back to x. Now I've got sine of theta equals x, so that means then that theta is the inverse sine of x. Now, to deal with this, I'm going to use the identity that sine of 2 theta equals 2 sine theta cosine theta. Because now I can come back to, I need 2 sine theta cosine theta, and I can just use my triangle. Sine theta is going to be x, cosine theta will be the square root of 1 minus x. Well, technically sine theta is x over 1. Cosine theta is the square root of 1 minus x squared over 1. So I'm going to put in, so that notice that the 1/2 and the 2, if I take this and put it in here, then the 1/2 times the 2 just gives me 1, and so I'm left with x times the square root of 1 minus x squared. All right, where x is sine theta and the square root of 1 minus x squared is cosine theta. And again, I want to put in -1 and 1. So this is 1/2, and I'm going to have inverse sine of 1 plus 1 times the square root of 1 minus 1 squared. That minus inverse sine of -1 plus -1 times the square root of 1 minus -1 squared. All right. Got all my parentheses and brackets in there. Okay, so this is going to clean up pretty nicely for us because 1 minus 1 squared is 0 and 1 minus -1 squared is 0. That's 0. That's 0. So I'm left with 1/2, and then the inverse sine of 1 is pi over 2 minus the inverse sine of -1 is -pi over 2. All right, so I have pi over 2 minus -pi over 2, which is the same as pi over 2 plus pi over 2, which is pi, times 1/2. That is pi over 2. All right, before I move on, I just want to come back to a geometric interpretation of this, because there was actually a much quicker way to figure this out. I'll just kind of do it in a different color to set it apart from the work that we've done here. If this is my function y, I have y equals the square root of 1 minus x squared. Then if I square both sides, I basically get x, and move some things around, I get x squared plus y squared equals 1. Well, so this y, well, okay, first let's graph this. That's a circle of radius 1. All right? And when I solve for y and just have the positive part of the square root, that gives me the top half of my circle. So we already know that the area of a circle with radius 1 is pi r squared, or just pi times 1 squared, so the area of the entire circle is pi, and since we're just taking the top half, then the area of the top half would be pi over 2, which agrees with what we found by substitution. Okay, so there's one example. You can see these examples can be a little lengthy, so I'm just going to do one more. Something that looks like this. So something a little bit different, we'll use a different trig function, and we also won't have just the straightforward substitution of u equals x. In this case, again, I have a function squared plus a number. All right, so we've already said that in that case, if I have something of the form u squared plus a squared, I know I'm going to want to use tangent. So let's go ahead, and I recommend to always set up a triangle because it's something you'll come back to. Notice here when I set up the triangle and I needed to go back to x to find sine and cosine, I just referred to my triangle, and it was very simple to find sine and cosine from that. So always set up your triangle. Theta is always going to go here, all right? And we know for tangent, my function is going to go over on this side, my number is going to go on this side, and this thing right here, this part that kind of indicates that trig substitution is the thing to do, is going to go right here, 4x squared plus 1. So what I want to do is take the square root of 4x squared and put that here. Well, that's going to be 2x, and the square root of 1 and put that here, so that's 1. So now I'm going to have tangent of theta equals opposite over adjacent, or just 2x. So x equals 1/2 tangent of theta, and dx equals 1/2 the derivative of tangent as secant squared theta, d theta. All right, so there is my substitution. So let's go ahead and put that in here then. So I've got the integral, we said dx, I'm just going to take that, well, we'll just put it in for right now, 1/2 secant squared theta, and I'm going to have this d theta out here, over, and we've got 4x squared. Well, if I take 2x and I square it, I get 4x squared, so 4x squared is the same as tangent squared. So I've got the square root of tangent squared theta plus 1. Okay, so now we have a trig integral. So let's look at how we can simplify this. First, I'm going to bring the 1/2 out. Integral secant squared theta over, and recall that tangent squared plus 1 is secant squared. So that's over the square root of secant squared theta d theta. Well, the square root of secant squared is secant, and secant squared divided by secant is just secant. So now I have 1/2 integral of secant theta d theta. All right, now you may or may not remember what the integral of secant is, but it's always something you can look up. It's probably worth knowing. So I'm just going to tell you what it is. It's the natural log of the absolute value of secant theta plus tangent theta. All right, and then I have this plus c because now I'm working with an antiderivative instead of a definite integral. Now finally, to finish this off, I started in x, I want to finish in x. So again, I'm going to use my triangle to determine what secant and tangent are. All right, well, secant we know is the hypotenuse over the adjacent, so this is going to be equal to this 1/2, and that stays the same, and then secant is hypotenuse over adjacent, or just the square root of 4x squared plus 1. Tangent is opposite over adjacent, or just 2x plus c. So that's my answer. It's not pretty, but it is the answer. All right, so again, the idea here, just coming back to our first page, is when we have something of the form, you're looking for a square root, and notice there could be other things in there, but it also includes this square root, right? Because we can always, as we showed here, we can always, after we find our substitution, we can substitute for x squared. That's not a problem. But we're looking for something that has a square root, and there's a function and a constant involved. If they're added, we're using tangent. If it's the number minus the function, we're using sine. And if it's the function minus the number, we're going to use secant.